All right, good afternoon, guys. Today we're going to talk about 4.2b. So let's get that started. Last time we left off, we were talking about what control groups were and placebo effects. Control group being something that you use to match your data to, so you can see if your variables actually had an effect on the group that you are providing that treatment to, as well as a placebo effect or a placebo, which means people think they're having something applied to them, or the individuals may believe they're having some kind of treatment, but in fact they are not. So it just kind of shows that you should have a group of no change. All right, so placebo effect describes the fact that some subjects in the experiment will respond favorably to any treatment, even in inactive treatment. So what that means is, like, for instance, there are some people who are hypochondriacs, right? They always think they're sick or they have some kind of disease, and they'll go to the doctor all the time. What doctors will do is they'll give the patient what's called a bread pill. At least they used to do this. I don't know if they do anymore, but they'd give a patient a bread pill. So they'd say, "Oh, this is what you need. This will help take care of your problems." And the patient would go home and take this pill that's literally nothing. It doesn't have any kind of medical benefits in it. And they would just take this pill and start feeling better. Like, they would legit feel poor. But it was just because they were convincing themselves they were sick. And now they've convinced themselves they have the medicine to be okay, and they start to improve. So a placebo effect means, like, you think you have the something that's going to change you, and the chemical makeup in your brain actually helps you improve. Now, it's not always in people, but in any kind of individual experiment, there can be a placebo effect where you see improvements despite the fact that the placebo is not supposed to do anything. A double blind experiment means that you are both hiding who has the treatment and who has the placebo from the individuals that are taking the treatments, as well as from the individuals who are conducting the experiment, right? So, say, for instance, I wanted to know if a certain pill worked really well, right? I wouldn't tell the doctors nor the patients who was getting the correct pill or the actual treatment and who was getting the placebo, because sometimes not only will the patients maybe respond differently to the questions you ask them later, but the doctors may also um, treat people differently in during that experiment. Or if a doctor maybe wants this pill to work well because they've got some money in it, or their friend is the one that developed it, or if they want to do poorly, then it might create some bias. So neither the people being measured, um, nor the subjects, okay, will know who, or people measuring nor the subjects will know who has the correct variable. In a single blind, either the subjects or the people who interact with them, one or the other, won't know who has a placebo and who has a treatment. So you have double blind and single blind. Pretty straightforward. All right. So when you design an experiment, one way you can conduct is called random assignment. To create roughly equivalent groups at the beginning of an experiment, we use random assignment to determine which experiment units get which treatment. So we don't want to say we're going to give the treatment to these people who are far more likely, maybe they're all athletically built, relatively young, no previous diseases, and then we give the placebo effect to, like, people who are sick or have diabetes, which usually has lots of health factors involved, right? And you're not, in that case, you'd be getting out obvious bias in your experiment because one group's going to do better anyways. So we want to use random assignment that puts them in groups randomly, not just based on whatever we decide. Okay. So use a chance process to put them in groups. So, for example, a total of 20 students have agreed to participate in an experiment comparing the effects of caffeinated cola and caffeine-free cola on pulse rates. Describe how you randomly assign 10 students to each of the two treatments. Okay. So there's three different ways you could go about this. You could use 20 identical slips of paper and just names down and separate them into two groups. That's random enough. You could use technology such as your random integers, right? And you would say the first 10, you're going to assign numbers to all 20 people. First 10 that show up are going to go into one group, or you could do every other. A lot of ways you can do it. Or you could do the same thing with assigning numbers and using table D. So, yep, group A, group B, your group P for placebo, group T for treatment. Anything like that would work. You could number people 0, 1 through 20 and then use random integer on your calculator, or you could use table D, which is to just say 0, 1 through 20 and identify the first 10 that you see to grow into group with caffeine. Pretty straightforward. Easy enough. Randomly assigned. Okay. An experiment control means keeping other variables constant for all experimental units. So we have some things that we need to keep consistent, right, or constant. After randomly assigning treatments and controlling other variables, treatment groups should be about the same, except for the treatment. So when we're looking at our two groups, you know how I mentioned we have like those with diabetes and those without, or those that are athletically built, or those that are not, right? You're going to have different groups. Well, outside of the two treatments being performed, we honestly want them to be almost all the same. So if we have 20 people, and we're gonna break them up into groups of 10 and 10 for that COLA experiment, we'd either want 20 people that are all healthy and young, or we'd want like 20 middle-aged people, or 20 older people, or 20 older people with a previous condition, right? We want them all to be relatively the same to each other. The only change we really want to see out of all these 20 people is just whether they have the treatment or they have a placebo. So you actually shouldn't be breaking them up and having this random groups of random different types of people. You should be looking for the same types of individuals, and everything should be the same except for those treatments. You can't say any difference in average response between treatment groups must be caused by the treatments, because there are always going to be some variables. Just because random assignment is unlikely to produce two groups that are exactly the same, right? In some cases, you probably can have groups that are exactly the same, depending on what your experiment is. But if you're doing anything with people or like plants or animals, there's going to be some changes in the two groups. So it's not going to always be a perfect, absolutely 100% guarantee experiment. So you can't say any difference is going to be observable, but what we look for in statistics is a statistical difference. Is there a clear and obvious difference between these two groups based on the treatment we gave? Okay, so in an experiment, replication means using enough units to distinguish a difference in the effects of treatments from chance variation due to random assignment. So we have a chance that each of these two groups are going to be different no matter what. Say we had a placebo group here and a treatment group here, but instead of this treatment group, we just gave the placebo to both groups. They're not going to have exactly the same data, right? Just by random chance, we're going to have changes in the two groups. So what we look for is something that we can replicate and get a repeated difference if we were to study this through two different groups repeatable times, okay? So can you replicate your experiment? Yeah, so we just need to make sure that we use enough subjects, really, is what we're looking for, okay? If you have too small of a sample, then you're going to have more chance of your results just being random. So if I did like 5 and 5, that's barely any subjects, right? And I'm going to have a lot of variation between how these 5 respond to my treatment or they respond to the placebo. If I did 50 and 50 and I see clear differences between the two subjects or the two groups, it's a lot easier for me to see that, okay, this is actually something that's been repeated by all these different subjects and confirmed by having larger numbers of subjects. Hopefully that makes sense. You just need to have large enough subject fields. Okay, I think we're going to stop there. 4.2C will move us on here. But yeah, really short lesson today. Mostly just want to get through some definitions, and I want you guys to go back and work through your projects, try to clean them up a little bit. I'll see if by the time class starts, I can get you guys some comments on your projects so far and some things to clean up. Sorry, I've been really busy. I was hoping to make this video over the weekend, but you know, busy stuff. So that being said, you guys have a great day. I will see you on Monday next week, and you guys just have one more class without me on Thursday. So I know you miss me so much. I'm sure. At least hopefully some of you do. All right. I'll see you guys. Have a great day.